Hello, welcome to lecture 8 of module 2, and this is lecture number 18 of the course. In this lecture, we'll continue our discussion on Josephson junctions. We'll see how Josephson junctions could be classified, and we'll discuss a few Josephson junctions, but in particular, we'll discuss the so-called transmon qubit. It's a Josephson junction in someone in great details because of its immense applications and relevance in circuit quantum electrodynamics. So let us begin. In the last class, we started discussing Josephson junctions. Josephson junction is basically two superconductors separated by a thin insulating layer. Earlier, we discussed the so-called Cooper pair box, which is a charged qubit. Apart from Cooper pair box, there are other kinds of Josephson junctions like flux qubit and transmon. And the development in Josephson junctions mainly came from the Ginzburg-Landau theory, which we discussed actually the main features in the last class. Previously, we learned about the BCS theory, and one of the main result of BCS theory was that the band gap in a superconductor is related to the critical temperature of the superconductor by this expression. And in the Ginzburg-Landau theory, however, it was they assumed that all these superconducting electrons are described by many particle wave function, say psi of RT, which is given by this expression, and here psi 0, this quantity is related to the local density of the superconducting electrons, and theta is the phase, and this theta, the phase is the same for all the Cooper pair electrons. Now, to understand the physical meaning of phase, this phase, one can use the so-called continuity equation for the probability of charged particle in an electromagnetic field, and we discussed that. We discussed that the continuity equation for the probability of a charged particle in an electromagnetic field is given by this expression, where rho is the probability density and J rho, this is the probability current density. And also we showed you that how one can actually get this continuity equation starting from the Schrodinger equation. Just I reminded you to how to get it, and the same strategy can be actually applied to get this particular expression that is written here, which is actually in the presence of a charged particle in the presence of a constant magnetic field. And the similar strategy applied, then we can get the continuity equation there, where this probability current density is given by this particular expression. Now, as Ginzburg-Landau theory says, that the local density of the superconducting electrons is given by the modulus of these wave functions, many particle wave functions, where this 0 refers to the number of condensate or superconducting electrons per unit area per unit time. And from here we can write down the current density. You see, there's a difference between probability current density and current density. Current density one can get just by multiplying by the charge, and which is again related to the velocity of the superconducting electrons and the local density of the superconducting electrons. Q is the charge here, and we can use the wave function as per the Ginzburg-Landau theory and put it in the expression here, and then we will get a couple of equations, and thereby finally we saw that this phase actually is related to the so-called, we can term it as we can give it a physical meaning in terms of, we can say that h cross great theta, where theta is the phase, is acting like a canonical momentum for these superconducting electrons. Now, then what we did, we went on to do the flux quantization and showed that the flux enclosed by a superconductor must be quantized in the unit of flux quantum phi 0 is equal to h by 2e, which we proved. To prove that, we have taken a superconducting ring pierced by magnetic flux, and we have taken a contour there, a curve there, which is a multiply connected region, okay, and far from the surface. And in this curve, both the current density and the magnetic field is zero here in this, along this curve C. And using this fact that the current density and the magnetic field is zero, we have utilized this integral and then put the expression for current density, and went on to obtain finally that indeed the flux is quantized, and this flux quantum is given by h by 2e. Then we discussed the so-called Josephson effect, and I forgot to tell you last time that it was discovered by Brian D. Josephson in the year 1962, and Josephson effect refers to the fact that it is a coherent phenomenon. It's which predicts a superconducting current flow between two superconductors separated by a very thin insulating layer. And we then try to discuss this effect very simply by using the a very simple model based on the Schrödinger equation. We have written this coupled Schrödinger equation for the we have taken two superconductors made up of the same material, and they are homogeneous, and they are separated by a thin insulating layer. And psi 1 refers to the wave function. Psi 1 refers to the wave function describing the superconductor 1. Psi 2 refers to the wave function describing the superconductor 2. And U1 and U2 are the ground state energies of each superconductor, and A is a parameter which characterizes the overlap between the wave functions psi 1 and psi 2, okay. And in fact, you can term A as the coupling parameter between the two superconductors. Then using the Ginzburg-Landau this wave function, psi 1 is equal to square root of n1 e to the power I theta 1. N1 is the local density of super electrons in conductor 1, N2 is the this local density of super electrons in superconductor 2. Theta 1 and theta 2 are the respective phases in the two conductors. Then we have put equation 2 in equation 1, and then after analyzing, we it turned out that the current density is basically a nonlinear function of the phase difference between the two superconductors, and Jc here is the critical Josephson current density. And another expression we got which relate how the temporal evolution of the phase is dependent on the difference in the ground state potential or the ground state energy. And if there is a potential difference between the two superconductors is there, then we saw that this phase difference between the two superconductors is given by this expression, where phi 0 refers to the DC phase, because if say you can see that if there is no potential difference V, then this phase is simply related to phi 0, which is the phase at time t is equal to 0, and current density is Js is equal to Jc sine phi, which I already told. So if the potential is 0, there is no potential difference is there between the two superconductor, no external potential difference, then there is a DC supercurrent across the junction. And in the presence of constant voltage, an AC current appears, which is quite evident from this expression. This expression we can further express in terms of the flux quantum. And finally, we saw that this Josephson junction is actually equivalent to a nonlinear inductor with inductance Lj given by this expression. Now let me discuss about the energy operator for a Josephson element. Energy operator. The energy operator can be deduced from the discreteness of the charge that tunnels through the barrier. Across this barrier, the charge getting tunneled from this side to that side or from the other side to this one. Okay, and the charge Qj that is tunneling through the barrier is an integer n times, n is a function of time, n times the charge q, and you know the q is basically twice that of the electron charge, q twice e into n of t. We can consider this n as an operator whose eigenstates correspond to the macroscopic state of a circuit with a well-defined number of Cooper pairs, such that we can define it in this form. So K10n, and n is the eigenvalue here. Okay, sum over all these things. So this is the operator we have. The tunneling Cooper pairs through the barrier can be translated into in a coupling between the eigenstates of the operator n, which can be expressed in this form. The Hamiltonian can be written in this form. We have Hj is equal to minus Ej by 2, and now this going from n is equal to minus infinity to plus infinity, and Cooper pair say is tunneling from one island to another one, and it has to be Hermitian, so we have to have a term like this as well. I think this should already remind you about what we have discussed about the tunneling part of the Hamiltonian in the context of Cooper pair box. And here this Ej is the Josephson energy, and it is basically given by this flux quantum into the current, critical current, divided by 2 pi, and this is refers to the so-called Josephson energy. This is Josephson energy. Okay, now this Hamiltonian here, this Hamiltonian can be written in terms of phase difference across the junction phi as well. So if we say introduce a new basis, say basis state, in terms of this is phi is the phase difference here. Now we are constructing a basis which is say it is in the basis of this number state I n phi. We define a basis like this, and is going from minus infinity to plus infinity, and you can see that under this sense, if phi goes from say phi to 2 pi, phi plus 2 pi, then this state phi remains unchanged, okay, or remains unaltered. It does not change. It's very easy to see. Or conversely, what we can define the number ket here, this as 1 by 2 pi 0 to 2 pi d phi e to the power minus I n phi phi. Okay, this is also in other in terms of this phase basis, we can write this number state basis as well. Now if we utilize this expression in our Hamiltonian that we have written, Hj is equal to minus Ej by 2, sum over n goes from minus infinity to plus infinity, and we have these terms here. Okay, this whole Hamiltonian that I have written here can be rewritten. So let me do that. Actually, okay, this is not difficult. We can some 2 or 3 steps I can take to show you explicitly. It is Ej by 2. Okay, Now let me utilize this definition. Okay, if you look at this definition here, I can write this guy as this summation sign. I can utilize it, only I have to multiply it by e to the power minus I n phi, because if I put e to the power okay, let me just show you, e to the power I n phi n, and this okay, this summation sign is also there. Okay, now summation of this guy with this one is already, we said this is ket phi. Okay, so hope you can see it. So therefore I can write, utilizing that expression, I can simply write this expression as e to the power minus I n phi, and this I can write as ket phi. I have utilized e to the power plus I n phi here. Okay, and then I am left out with this one, n plus 1, the bra part, and similarly here I can write it as e to the power minus I n plus 1 phi, and this guy I can write it as ket phi, and then I have this bra n here. Okay, and now let me utilize this one is a by 2, and as per my, let me introduce this one now. That would be 1 by 2 pi, okay, 0 to 2 pi d phi e to the power I n plus 1 phi, because now I'm taking the bra of this one, so here it is minus, now it would become plus because I'm just dealing with the bra part here, and I already have e to the power minus I n phi, and then I have here this ket phi and this bra phi. I hope you are getting it. Similarly, in the next term I can write plus e to the power minus I n plus 1 phi, that is already there, and I have this ket phi, and for the bra n I can write this one, I write 1 by 2 pi 0 to 2 pi d phi e to the power I n phi, this is bra phi. Okay, this is what I get, and you can easily see that whole thing I can write it as minus ej by 2, 1 by 2 pi, and then I have 0 to 2 pi, this is d phi, and I have terms e to the power I phi plus e to the power minus I phi. Okay, and then I have this ket phi and bra phi, and okay, so this is what I get. Now if I introduce a new operator, let me introduce a short notation, or say, because you see this is an operator, if I introduce the operator, say e to the power I phi cap, that if I defined this quantity as 1 by 2 pi 0 to 2 pi d phi e to the power I phi, this ket phi bra phi, and this I write it, define it as this operator e to the power I phi cap, then you can easily see that this Hamiltonian I can write in a more simpler form, a compact form, that would be minus ej cos phi cap. Alright, so this is the another way to express the this tunneling part of the Hamiltonian, or the Hamiltonian for the Josephson element. Now this operator phi cap, the phase operator, is the phase conjugate. This is the phase conjugate of the number operator n cap, and in fact this is reflected in the commutation relation between phi cap and n cap, and they don't commute, they are uncertain, they are conjugate variables. And Now this can be used to obtain this commutation relation can be used to along with another fact that suppose this n couples linearly with the voltage operator through the Cooper pair charge 2e, then using these two facts one can actually obtain the quantum version of the Josephson equation which we wrote earlier. Js is equal to jc sine phi, and where this phase phi is equal to phi 0, and you recall that that this is actually at phase at time t, and it is associated with the phase at time t is equal to 0. It is charge divided by h cross and integration of v of t dt. Now all these quantities would become operators, and this voltage operator is going to be coupled linearly with this number operator, and it would get coupled through the, as I said, through the Cooper pair charge 2e. Now generally the Josephson element that we discussed, and I already told that this Josephson element is termed as the nonlinear inductance Lj, right? And the term Josephson junction, on the other hand, this term Josephson junction is reserved for the physical realization of the junction and which is generally modeled by a capacitor, say C, because this is Josephson junction, so let me write say Cj. This capacitor is connected to a nonlinear inductance Lj in parallel. So this is the model diagram for a Josephson junction for the physical realization, and it is nonlinear inductor, so therefore this is the symbol that is used. But actually symbolically it is represented in a more simpler form, and you just have to this is denoted in literature simply by this cross. Okay, this cross actually refers to the nonlinear inductance or the Josephson element. Okay, now let us now briefly discuss about various superconducting circuits. Now we are going to discuss various superconducting circuits, and all of us already know that the qubit is a fundamental element in the field of quantum information, and it's basically nothing but a quantum two-level system, and one can take advantage of the Josephson junctions to build a two-level system that will be called superconducting qubit. Actually, rather, let me say not circuit, let me say I'm going to discuss about superconducting qubits. The Josephson junction, as I said, let me write again, the Josephson junction is a nonlinear inductor in parallel with a capacitor. Okay, the nonlinearity here actually means that the energy levels are not regularly spaced, because as you see that this is basically an LC oscillator. This Josephson junction is an LC oscillator, and you know the LC oscillator is a harmonic oscillator. If it is a linear harmonic oscillator, we know that in the linear harmonic oscillator all the energy levels are equally spaced. This is linear harmonic oscillator, all the energy levels are equally spaced. But when we have a nonlinear element like this Josephson element or nonlinear inductor, what happens is that this harmonic ladder is become anharmonic, and this we don't have equal energy spacing. Rather, what we can do, we can have a specific parameter circuit configuration. We can take it in such a way that we can obtain these two low-lying energy states, and that can be separated from all the higher energy levels by a huge gap. And in that case we can consider this whole structure as a kind of a two-level system, because then we can simply focus on only on these two energy levels. So under the so-called two-level approximation, this Josephson junction will behave like a qubit or a two-level system. In fact, when a circuit is composed by Josephson junction, we know that the Hamiltonian, which we discussed earlier, the Hamiltonian has two parts. One is the charging energy part, so that is a half q square by 2c. Here it is a Cj, and we have another part is because of Josephson tunneling, that is generally written as Ej cos phi by phi 0. Okay, and or we can can also be written as h is equal to Ec n square minus Ej cos phi by phi 0. And here actually I have utilized the fact that Q is equal to twice E, the electron charge, into the number operator, number of Cooper pairs, and here EC, as you can see, this would be simply twice E square divided by 2Cj. So this is you can recall that similar kind of stuff, and there is actually some convention is there. Some people write it in different way, but essentially this EC basically refers to the charging energy. EC refers to charging energy, and EJ refers to, so EC refers to charging energy, and EJ refers to the Josephson energy. It is Josephson energy. And these Josephson junctions are, or superconducting qubits, are classified according to this ratio. So superconducting, let me just write here that superconducting circuits or qubits are classified according to the ratio Ej by Ec. I will give some example, then it will be more clearer. For example, we have the so-called charged qubit, and which is also known as CPB qubit, Cooper pair box qubit. In this case, this ratio Ej by Ec is less than 1, and this clearly shows that this actually implies that the charging part of the Hamiltonian, charging energy dominates over the Josephson energy, which is actually called flux energy, you can say, or you can simply say Josephson energy. And it actually consists of a small superconducting island placed between the barriers of the Josephson junction and a plate of a capacitor. So this is what we have. This is one of the plate of the capacitor, this is the other plate of the capacitor, and this is the Josephson junction. Okay, and then they are connected by gate voltage, say Vg. So this is the symbolic representation or diagrammatic representation of a charge qubit here, and sometimes some people also represent it in this form also. And this is the box, it is CPB, or it is called a charge qubit, because in this case, as I said, this is more charge contribution to the energy dominates over the flux. And in fact, you can recall that when we discussed Cooper pair box, there we said that the tunneling part of the Hamiltonian acts like a perturbation. Now applying this voltage, a charge difference between the two sides of the Josephson junction, right, is induced, and thus the qubit can be, so this charge qubit, the charge qubit can be controlled by electric fields. Okay, there is another qubit, and that is called the flux qubit. And you can guess that in the case of the flux qubit, the ratio is the opposite. EJ by EC is greater than 1 here. And in fact, this is basically a superconducting ring like this, and it is interrupted by 1 or say 3 Josephson junctions like this. So this is what the flux qubit. And here EJ is greater than EC, so clearly the Josephson energy dominates over the charging energy, and this is getting coupled to a external magnetic field. This is getting coupled to an external magnetic field, that is the magnetic flux Phi that actually flow across the closed loop, and this flux induces two circulating supercurrents. One may be in this direction, one current may be in this direction, the other may be in the other direction. Okay, these two superconducting currents either clockwise or anti-clockwise, and this is going to define a qubit. So it actually, let me write here, the flux, this external flux, this flux induces two, let me write it more clearly, this flux induces two circulating supercurrents, supercurrent states rather, supercurrent states. Okay, so supercurrent states, and this may be either, as I said, either in the clockwise or anti-clockwise direction, and this is going to define the qubit. Another one is the so-called phase qubit, and in the phase qubit, it basically consists of a single Josephson junction. So you have a Josephson junction like this, and this is connected to a current source. Okay, this is connected to external current source. This is current source, and this is the Josephson junction. So this qubit actually profits from the phase difference phi of the Josephson junction in the regime here. EJ by EC is much larger than 1, that, and it is affected by only flux fluctuation. Now, one particularly important qubit is the so-called Transmon qubit, and which is heavily used in circuit quantum electrodynamics, Transmon qubit, and this is what we are going to discuss somewhat in details now. We can represent the physical picture of a Transmon qubit, physical picture of a transmon qubit by this diagram. So this is one representation of transmon qubit. As you can see, there are two metallic pads or islands, say metallic island number 1 and metallic island number 2. Actually they are superconductors, and they are connected by a junction, and this is basically a nonlinear inductor. Actually it is a Josephson tunnel junction. Okay, you can imagine, just like in Cooper pair box, Cooper pair to tunnel from the first island to the second island, which make the first island to have a net positive charge q of t. And as you know, the whole structure could be described in terms of charge q of t and current I of t. So the whole structure would have these quantities. You can represent them by q of t, the charge, current I of t, and there is a voltage also, there is v of t, and also the magnetic flux phi of t. So these are the four quantities by which you can define this whole structure. In fact, you know that some of these quantities are related to each other. For example, the magnetic flux phi of t is nothing but the time integral of the voltage, that is v of t dt. Integration is from, say, minus infinity to some time t. So in that case, let me write it like this. And or we can express the voltage as the time derivative of the magnetic flux. From our previous classes, we know that this structure could also be represented by a circuit comprising of a capacitance and an inductor but here, as I said, the inductor is a nonlinear inductor. So generally this is, as you know, it is represented by this symbol, and we have these two terminals. This terminal 1 and 2, you can consider it to be 1 as the metallic island 1 or the superconducting island 1, and the 2 as the superconducting island number 2. And this nonlinear inductor, the Josephson junction, is described by a magnetic flux phi. In fact, you know that LC circuit is a harmonic oscillator if inductance is a linear inductor, but because the inductor is now a nonlinear inductor, so this becomes a nonlinear oscillator. So in other words, we can say that the transmon is a nonlinear oscillator. Alright, before I proceed further, let me show you a picture of a real Josephson tunnel junction. So here it is a picture of a real Josephson junction, Josephson tunnel junction, and it is a picture of a scanning electron microscope or an SEM image. If you look at this image carefully, you will see that there are two pieces of metals, say metal number 1, actually superconductors, superconductor number 1 and superconductor number 2, each having a width of approximately 200 nanometer. This one is, its width is 200 nanometer. Here also the width is around 200 nanometer, and they are falling on top of each other. Between them there is some kind of a barrier. If you look at it, you see there is some kind of a barrier. This is an oxide barrier and it's an insulator. Details, however, does not matter. The key point is that because of this barrier between the two superconductors, which we can denote as terminal number 1 and terminal number 2, okay, terminal number 1 and terminal number 2, and the junction we can represent it by a cross sign like this. So this is what this Josephson tunnel junction is. This element can be represented by an energy function that only depends on the change in the magnetic flux across the terminals, across these two terminals, and this energy function is given by E of phi of j, that is the energy, it's a function of the magnetic flux. It is equal to minus Ej cos phi j divided by phi 0. This is the energy function. Here Ej is the so-called Josephson tunneling energy. This you already know. This is Josephson tunneling energy. And phi j is the magnetic flux which is scaled. Phi j is scaled in terms of the flux quantum, in terms of the flux quantum phi 0, which is, you know that it is h by 2e. Now after having this energy function, we can write down the Hamiltonian for the transmon qubit. The circuit diagram for the transmon qubit is this. We have this capacitance and we have a nonlinear inductor now. And the Hamiltonian would be h is equal to q square by 2c minus Ej cos of magnetic flux divided by the flux quantum. And we have, as you see, we have a charging energy term and a tunneling energy term. Okay. Let us look at the tunneling energy term, which is due to the nonlinear inductor. We can break this energy function Ej cos of phi j by phi 0, we can break it into a linear and a nonlinear part. If I expand this function into a Taylor series, we know the expansion of cosine function. The expansion of the cos function would be 1 minus phi j divided by phi j square divided by 2 phi 0 square. Then we have 1 by 4 factorial phi j by phi 0 to the power 4, and then we'll have higher order terms of the order of phi to the power 6. But we are going to ignore all the higher order terms beyond phi j to the power 4, and then we can express the transmon Hamiltonian as follows. We'll have h is equal to q square by 2c minus Ej plus Ej, all these are operators, phi j square by 2 phi 0 square minus Ej by 4 factorial phi j to the power 4 divided by phi 0 to the power 4. Okay, we are ignoring all higher order terms as I already said, and also we can ignore this term because this is simply an energy offset term. On the other hand, the term, if you look at this term, we can rewrite it as follows. This particular term Ej into phi j square divided by 2 phi 0 square, I can write it as phi j square divided by 2Lj, with Lj is equal to phi 0 square divided by Ej. In fact, this term should remind you about the energy stored in a linear inductor, and we can name Lj as an linear effective inductance. So this is linear effective inductance. Therefore, we can write the Hamiltonian in this form now. H is equal to q square by 2c plus phi j square by 2lj minus ej by 4 factorial phi j by phi 0 to the power 4. Okay, what you see here, that there is a part in the Hamiltonian which resembles the linear harmonic oscillator. It will remind you about linear harmonic oscillator. And on the other hand, there is another part that is due to the non-linearity. Okay, now we can borrow our mathematical apparatus of creation and annihilation operators from our knowledge on quantized harmonic oscillator. And in analogy with the mechanical harmonic oscillator, we can see here that the magnetic flux phi j plays the role of coordinate. Therefore, we can define phi j in terms of creation and annihilation operator in this form. That would be phi ZPF, that is the 0-point fluctuation of the magnetic flux, into A plus A dagger. And then the linear part of the Hamiltonian one can easily write, that would be H is equal to H cross omega 0 A dagger A, and the nonlinear part is minus Ej by 4 factorial phi ZPF to the power 4 into A plus A dagger to the power 4, where this omega 0 is equal to 1 by square root of LJC, and this term phi, without these symbols here, you see, without this dash sign, this is normalized 0-point fluctuation, and it is equal to phi ZPF divided by the flux quantum phi 0. Okay, now this normalized quantum fluctuation is mostly it is very small, and taking this into account, let us now first focus on this particular term, this nonlinear term, A plus A dagger to the power 4. We can expand it, and because these are operators, while expanding it, one has to be very careful. When we take the multiplication, we have to multiply it as per the order, and if we expand the whole thing, please try to do that, you will get all these terms. Let me write down. You will get A to the power 4 plus 6 A square plus 12 A dagger A plus 6 A dagger square plus 3 plus 4 A dagger square A square plus 6 A dagger square A square. In fact, this is 4 A dagger square A. You have to be careful. Okay, let me correct it. This would be 4 into A dagger A cube. Please verify it yourself, and you will get 4 A dagger cube A and A dagger to the power 4. So all these terms you will get, but you need not have to worry, because quite a number of terms can be dropped from this expansion, invoking the so-called rotative wave approximation. For example, you see, let us look at some of the terms. Say a square term. You know that the annihilation operator, it evolves in time as per e to the power minus I omega t, right? So therefore a square, this term is going to evolve in time as e to the power minus twice I omega t. So therefore a square is a oscillating term. It oscillates with frequency twice omega. Similarly, if you look at the term say a dagger a cube, a dagger oscillates as e to the power I omega t, and a cube oscillates as e to the power minus 3I omega t, so with frequency 3 omega. So overall the whole term oscillates with frequency twice omega. So this way you can analyze it, and you will find that there will be lot of terms which should be rotating, and there will be couple of terms which are non-rotating terms. And as per the rotating wave approximation, you neglect all the rotating term and just okay, let me here write down once again the whole thing. Okay, rather than doing this, let me show you here. This term would rotate with frequency 4 omega. So we can neglect that, we can drop that term. This term is going to rotate with frequency twice omega. This term is a non-rotating term. This term will rotate with frequency twice omega again. We can drop that term. This term we can also drop because this is simply an energy offset term. This term is also going to rotate with frequency twice omega. We can drop that. This term is not going to rotate because a dagger square and a square, they will nullify their rotations. Again, this term is going to rotate, so this we can neglect, and this term is also going to rotate with frequency 4 omega. So that way we can drop all the rotating terms and we can just keep the non-rotating terms, and here will be left out with only these two terms. So therefore we can finally write down the, using that we can write down the RWA Hamiltonian, the Hamiltonian for the transport under rotating wave approximation as h cross omega 0 a dagger a minus Ez by 4 factorial phi to the power 4 ZPF, and here we have term 12 a dagger a plus 6 a dagger square a square. All right, now okay, let me simplify this further. We have h cross omega 0 a dagger a minus Ez by 2 phi ZPF to the power 4 a dagger a minus Ez by 4 phi ZPF to the power 4 a dagger square a square. Now if we define certain quantities, we can simplify, we can write the transport Hamiltonian in a very simplified form. If we define say h cross alpha is equal to Ez by 2 phi ZPF to the power 4, which I can also, it is, if I equate it to a term h cross delta q, its significance would be clear to you soon. Then we can write the transport Hamiltonian under RWA rotating wave approximation as h cross omega 0 minus delta q a dagger a minus h cross alpha by 2 a dagger square a square. So this is the form of the transport Hamiltonian we finally obtained. We will continue our discussion of this transport Hamiltonian in the next class. Before I stop, let me make a couple of comments about this Hamiltonian. You can see that from the first term in the Hamiltonian, the frequency omega 0 of the linear harmonic oscillator is now modified by delta q, and this can be attributed to the 0 point fluctuation of the magnetic flux, as you can see that delta Q is related to this normalized 0 point fluctuation of the magnetic flux, and many a times this phenomenon is referred to as Lamb shift. On the other hand, the last term in the Hamiltonian is there completely due to nonlinearity. This term is completely due to nonlinearity. Okay, let me stop here for today. In this lecture, we discussed various Josephson junctions very briefly, and we learn how to classify a Josephson junction. It's basically depends on the ratio of the Josephson energy and the charging energy. In particular, we studied in somewhat details about the Transmon qubit. It's a Josephson junction, and we in fact derived the Hamiltonian describing the Transmon qubit. In the next class also we'll continue a bit of discussion on Transmon qubit, and it will be followed by a discussion on how to incorporate dissipations in our formalism, because so far we have not taken into account any kind of quantum dissipations or dissipative effects in our formalism, and this is what we are going to do in our next class. So see you in the next lecture. Thank you so much.